So again, something a little bit different than we usually do. I don't know if anybody watched the Olympic women's hockey game last night, or if you know what the results are, but I have some highlights that we can watch. Yeah. You guys know that I'm a big hockey fan.
Yeah, it was pretty.
Hold on. Yeah, it's the final. Yeah, that was it was a tip. Might have been the bad guys that scored there, but that was a good shot. That was a really bad change. I can do that. All right, so this was actually the first time the Olympic women's team won gold since 1998, so it's been 20 years since we won that game. So congratulations to the women's hockey team. I was on Facebook this morning, and one of my friends that I played hockey with in high school posted a sentiment that I can second. That's right here. So in honor of the Olympic women's hockey team and their victory, we're actually going to use hockey and a hockey stick to talk about Lenz's law and magnetic inductance. And we'll see how that's going to go once we get there. But to start with, what we'd like to do is we'd like to talk about how we can conceptually think about the current that goes around a loop of wire and how that can be related to a bar magnet. So a lot of these experiments that we're going to do and a lot of the calculations that we're going to do, your intuition will be better if you replace a loop of wire that has a current going through it with a magnet, because then you can say, okay, if I have two north sides of magnets, we know they're going to repel, and if they're south and north, they're going to attract. So you have a little bit better intuition if you can figure out how you can replace loops of wire that have currents going through it with bar magnets. So go ahead and consider this north-south bar magnet here, and we want to draw what the magnetic field lines look like and then compare that to what the magnetic field lines look like for this loop of wire that we have drawn here. Okay, so take a little bit of time to do that. And talk about this one. So we had this loop of wire drawn like this, where we had the current going around like this, and we saw that the magnetic field lines are going to look like this. Now, if we consider our bar magnet that we had here, where this is some north side and this is some south side, the magnetic field lines actually look almost identical to this, because we know that the field lines go away from the north side and they go towards the south side. Okay, so when we're doing these conceptual arguments with Lenz's law and trying to consider how how the induced current is going to look relative to a bar magnet. That's going to help us to conceptually understand the forces here. So this is going to lead us into our hockey demo here. So in order to demonstrate Lenz's law, what I like to do is I like to get some volunteers. So I need 3 people. 1, 2, and 3. Okay. So Lenz's law is kind of a qualitative statement of a more general equation called Faraday's law, which we're going to discuss more today. So I want you to be a loop. So you're just a loop. Okay. This I'm going to treat as a bar magnet. So this is going to be the north side of the bar magnet. And we want to consider what the direction of the magnetic field is from this first. So if this is the north side, what's the magnetic field going to look like from it? It's going to go this way, right? So when we think about changes in magnetic flux, the statement of Lenz's law is that nature abhors changes in flux, and it acts in such a way to oppose those changes. So I'm going to have you be a magnetic field, and you're going to be a direction of a current. So we have our loop here. And so if I bring my magnet here, what's the direction, and I'm pushing it this way, what's the direction that the magnetic field that the loop makes is going to go? It's going to go this way, right? So what direction of current do we need to have in order to produce a magnetic field that goes that way? So you're the current. Go around the loop the way that the current's going to go. So our magnetic field, I'm bringing it in this way. I'm bringing it in this way. So our magnetic field, you're pointing this way. And so what current can I put in this loop to make a magnetic field that goes that way? It's gonna go around like this, right? So come over here and you can go around like this. So that's our current. So I'm pushing the magnet this way, which is going to induce a magnetic field that opposes that change, and then it's also going to induce this current. So if I go the other way, so this is my south side now, and I'm putting the south side this way. What's the direction the magnetic field is going to point that's induced, right? So south side, the magnetic field is going to go this way, and I'm increasing that way. So yeah, it should go this way. So then the current is going to go which way? The opposite way. Good. So go ahead and give our volunteers a hand. So when we're considering what the direction of the induced current is and what the direction of the induced magnetic field is, think about that conceptual example that if I'm increasing the amount of magnetic field going in one direction, I haven't done that in a while. It was overdue, right? I did it last class. Fine. Somebody's keeping score over here. Okay. So when we consider increases in magnetic field in some direction, we know that nature's going to oppose that, so it has to do something to balance out that increase, and that's going to induce a current that creates that magnetic field. So let's come back to one of the demos that we did at the very beginning of our discussion of magnetic fields, and put this together with how we understood the direction the current goes and how we can consider that to be like a bar magnet. So go ahead and talk about this question. I think we already know what the answer is, but the next thing that we want to do is we want to apply this understanding of Lenz's law to determine what the direction of the current has to be in order to oppose the change in magnetic field produced by this north side magnet moving down. Okay, so go ahead and talk to each other for a little bit about this one. Okay, so what do we say about this one? Does it take more time or less time to travel this distance? It takes more time, right? And we can show that. So here's the north side's pointing down, and so if I just drop it, I'm probably not fast enough to jump down there and catch it. But if I put it in the tube, it takes a long time, right? And that's because ultimately what I'm doing is I'm inducing a current in this tube when I'm changing the magnetic field by moving this magnet. And so what we want to do is, based off of that observation that we had, knowing that it's going to be moving slower, we want to determine what the direction the current is going to go in this, as this north side is going down through here. Okay. So go ahead and talk to each other about that, and think about the argument that we made with the qualitative example that we did. So really, when we're talking about this tube, what we could treat it as is just a giant stack of loops, right? So this is really like having like a whole bunch of loops on top of each other. But in order to figure out what the direction the current goes, we could consider just having one loop, right? And so we know that if I have the north side of the magnet pointing down and I drop it, then the magnetic field is going to increase going down as I'm moving this down. And so nature wants to oppose that change. And so the way that it can do that is to say, I'm going to have some current going around this loop so that the magnetic field is going to be pointing up. So it's going to oppose that change. So the induced magnetic field, B induced, is going to be up. Okay. So that's a D, not a CT. So what that means is if the magnetic field is going to be pointing up, we can figure this out a couple of different ways, and I want to be careful with our right-hand rules, because when we found what the direction of the magnetic field was from a long current-carrying wire, what we did was we pointed our thumb in the direction of the current and then curled our fingers around in the direction of the magnetic field. We can do the same thing here. So if we know that this is going to be up, then whatever direction I curl my fingers, I'm forcing my thumb to point in some direction. So if it curls up, that means that my thumb is going to point around this in this direction. So this is going to be this way. Okay. Now the other way that you can do this, and again I want to be very careful because when you can confuse yourself if you mix the rules in different ways. The other way that you could think about this is if I have some loop like this, I can take my fingers and I can point them in the direction of the current, and my thumb points in the direction of the magnetic field. So if my thumb is then pointing in the direction of the magnetic field, then my fingers will curl around in the direction of the current, and so that means it's going to go around this way. But like I said, be careful with that, because if you're in the mindset that I say I'm always going to have my thumb as the direction of the magnetic field when I'm dealing with magnetic fields and currents, then you might confuse yourself with these. So just make sure that whichever way you choose to approach this problem, that it gives you some consistency with what Lenz's law tells you. So what that means here, if this is going to go around this way and the magnetic field points up, that's the same thing as having the north side of a magnet and a south side of the magnet like this, right? And this gives us some understanding as to why it takes longer for this to go through here. Because if each one of these little loops is like having a north magnet pointing up, and this is a north pointing down, then they're going to repel each other. And so that's why we can understand, that's how we can understand why it takes longer to go through the tube. Now, what I want you guys to do is I want you to go through the same argument again, if instead we flip it so that the south side is pointing down. So how is this argument going to change if we have the south side pointed down? So go ahead and talk about that. So let's go ahead and talk about this one. So some of you might have had the intuition that it's just going to be the reverse of what I had said last time, and that's true, but we want to be able to explain why that's true. So we can approach that from two different perspectives. One is the perspective of Lenz's law, to say that the induced magnetic field should oppose the change, and the other way to go about this is to talk about it in terms of these bar magnets, and knowing that it has to go slower when it goes down, which means there has to be a force that opposes this motion, and then we can figure out what the direction of that bar magnet would be, and then we could draw some associated loop for it. So let's talk about it from both perspectives. So if I have this south side going down, right? The magnetic field from this is going to be pointing up, but as it's moving down, it's becoming less up than it was before. So what that means is whatever direction this loop is going to go, it needs to oppose that change. So what that means is I need to have this going around in this direction, right? So it goes around this way this time, okay? So that the induced magnetic field is going to be going down. So this is B down, B induced, okay? Now we can see how that's consistent with our bar magnet here, because if we know that the magnetic field leaves the north side and it goes towards the south side, so it leaves the north side, so this is the same as this. Now, to bring that around to the way that we could talk about this in terms of forces in the north and south side, we can see that this south here will repel this south here. And so that gives you some understanding of why it's going to take longer to go from the top to the bottom. Okay, so this can be a little bit confusing, and we're going to have some more practice with it as we go. But the next thing that I want to do is I actually want to talk about magnetic flux, because we hadn't talked about magnetic flux in a lot of detail, and that's going to be important for these calculations. So conceptually, what flux is it's an amount of field lines that go through some area, okay? So we're going to do our favorite calculation that we always do, and so I give you this equation for magnetic flux. I want you to find what the units of magnetic flux are, okay? So I also, we have the exams here, so I'm going to call you up row by row to pick those up. So the first row of people here, you guys can pick up your exams. They're in alphabetical order, starting at A here and going this way. So as far as the dimensional analysis questions go, I think this one's pretty easy, because we know that the units of the magnetic fields are going to be Tesla. So this is units of Tesla. So B is in units of Tesla. And A is an area. So this is in units of meters squared. What are the units of cosine of theta? Dimensionless, right? So cosine of theta, or any trigonometric ratio that you have, it really is it's a ratio, right? Because it's cosine is the adjacent divided by the hypotenuse, right? And so that adjacent has a unit of meter, the hypotenuse has a unit of meter, and so since it's a ratio, those are going to cancel. And so that means that the units of our magnetic flux are just going to be Tesla times meters squared, okay? So now we want to actually do a couple of calculations with this. So I'll give you three situations here. I tell you that we have some loop of wire that has some radius of 5 centimeters and some magnetic field of 10 Tesla. And we want to find what the magnetic flux is in these three situations. Okay? So go ahead and talk about that. I think once we explain it to you guys, it seems to make sense. But I think the thing that's kind of tricky here is what is the angle of theta? What does it mean? How does that relate to the loop, and how does that relate to the magnetic field? And so I'll talk about it both in terms of the equation and then in terms of what flux really means. So for the first question, what it says is that the loop is in the plane of the page. It's like this, and the magnetic field points out of the page. Okay, so what that means then, I'll find some chalk. What that means then is that the area vector, by definition, is always perpendicular to the loop. So the area vector I could call A vector for all of these questions is going to be pointing out. like this, okay? So in order to calculate the magnetic flux for the first one, we'll say this is part A, this is going to be equal to the magnetic field B, so this was 10 Tesla, times the area of the loop, so I tell you this is 0.5 centimeters, so this is pi times 0.05 meters, so this is 0.05 meters squared, and then times the cosine of the angle between this area vector and this magnetic field vector. Now since these are in the same direction, that means that angle is going to be 0. Okay, and so I don't have the answers written down here, but you can plug this into your calculator, and then that number will be the answer here. So the next one, when we look at B, and I should have used different letters because we have A's and B's for the area and magnetic field, and A's and B's for the indices here. Things to learn for next time. So the calculation looks almost exactly the same. So we have our magnetic field 10 Tesla. We have the area pi times 0.05 meters squared times the cosine of the angle between them. Now in this case, I tell you that the magnetic field points to the right. So what that means is that A points this way, magnetic field points that way. What's the angle between them? It's 90 degrees. So this is cosine of 90. And so this one is equal to 0. Okay? The last one, phi c, I actually just tell you what the angle is, and so what that means is you can do this calculation just by saying this is 10 Tesla times pi times 0.05 meters squared times cosine of 37 degrees. Okay? And then that's it. Now, the thing to take away from this is, you know, it's good to be able to do these calculations, but the real physics is understanding what each one of these mean and how they relate to each other, right? So when I see that I do these calculations, I can rank these to say which has the largest and which one has the smallest flux. The smallest flux is going to be B. So this is the smallest, and then C, and then A. So the flux for A is the largest. So let's see what that means. So when we're calculating flux, what it's really saying is how much of the magnetic field goes through this loop. And if the magnetic field is in the same direction as the area vector of the loop, all of it's going to go through, right? Now if it's coming on this way, and this is the direction of the area vector, none of it's going to go through the loop, right? And if it's somewhere in between, it's going to be somewhere between that maximum and that minimum. So that's really what we're getting at in trying to understand what this cosine of the angle means, okay? Any questions about this? Okay, so we're going to spend some time working on the packet that we started on Tuesday, and then we're going to come back and do another demo at the end. Okay, so take out those packets and we'll keep working on those.